Welcome everyone, my name is Garry Thu. I am your EE Technical Lead for ASME this year. Today is our first workshop and we're going to be going over motors. This is the only workshop where it's going to be pre-recorded. However, when it comes for the following 3 workshops, everything is going to be live, but at the same time, it will still be recorded so you guys can rewatch it later. So after the 4 workshops, what's going to happen is that we're going to have projects assigned to you guys, and I believe there's going to be about 3 EE projects, and you guys can pick which one. And if we have a big team, it will be like kind of divided up into teams. If we have a small team, then individually, each person are going to be in charge of a project of its own. So I'm really excited to work with you guys, so let's begin. All right, let's see. Okay, like I said, my name is Garry Thu. I am actually a 4th year at Cal State LA, majoring in mechanical engineering. I know I am leading an electrical technical workshop, but I'm a mechanical. That doesn't, so again, this is here to reiterate that it doesn't matter what background you have, you guys can dive into whichever area of you feel that you want to be with, okay? So that's another iteration, okay? So again, I'm a 4th year at Cal State. I'm going to be graduating this year. So if you guys have any questions about what classes to take and anything like that, you guys can also ask me questions about that too. I am more than welcome to help you guys with anything, even outside of ASME as well. Okay, here we go. Okay, so this is the agenda of today's workshop. I'm going to go over 4 different types of motors. First of all, it's called brushed, brushless, servo motors, and stepper motors. Those are the fundamental ones. There's obviously a lot more out there, like for example AC motors, but we are not going to go over them today or in this workshop because it doesn't really apply to us for our robots. We are actually going to be using brushed DC motors, so there's going to be a heavier emphasis on what those motors are about. All right, so let's get into it. Of course, we're going to talk about motor drivers as well as some of the motor specifications of the one that we picked out for the competition. All right, here we go. Okay, so we're going to talk about brush DC motors, and it's rather one of the most common type of motors out there, and here's why. So let's look at the inside of these DC motors first. What you see right here that I'm pointing with my arrow, let me actually get a pen so I can like highlight it for you guys. All right. I like to be green. All right. So what you see right here, oh, I don't think that was the greatest color there is. Let me see. There it is. This color right here. These two parts right here are called permanent magnets, okay? And then the one in the middle are called armature coils, because first of all, it's an armature and it's being coiled up with copper coils. Why coppers? Because it's conductive, okay? Okay, so that's one side of the motor, and what you see on the other side are actually brushes, okay? This is why it's called brushed. These black little parts right here that you see are called brushes. And essentially what they do is rub against this copper covered shaft, so that the electricity that's being fed through the wire can energize the coils on the armature, and which in turn rotates the armature, and then basically what you got is a motor then. So that's essentially how the brushed DC motors work. So what's the downside of, what's the advantages and some of the disadvantages of brushed DC motors? Well, let's take a look. Well, advantages are the fact that it is inexpensive, it is lightweight, and is reasonably efficient. And most important of all, this is particularly why we picked this motor, is because it has good low speed torque, okay? Now, why does that matter? Well, for us in our competition, what we're dealing with is a robot that's on the floor, and more importantly, the robot is going to be on grass, so it's going to be slippery, and if the robot is heavy, it needs to the motors need to provide a lot of torque so the robot can move. And why is it a good thing that it's low speed? Well, it needs to be because the robot doesn't need to be going very fast for a competition, and that means that we can actually slow down the robot however we want, but not too slow. Of course, there's a thin line of how slow we can go. But what I'm trying to say is that it needs to have a good torque. Like, it shouldn't lose torque power as it gets as it gets slowed down. So hence the reason why we're actually going to be using this motor, because even at low speed it can still provide a good amount of torque. That's a real important part. All right. Now, what are some of the disadvantages? Well, what you gotta notice is that these brushes can wear out over time, because due to friction, these are going to disintegrate and then get smaller and smaller, and eventually at one point they're going to be gone, and you're not going to be able to transfer electricity through the copper brushes and onto the armature coil. So over time these do wear out, and when they do wear out, you have to replace them. And placing that, this is why it's okay for you to this is why it's preferable that it's inexpensive, because you can easily replace them. Now, this is not true for back in the days, because they do have an industrial size DC motors, and for those industrial DC motors, you can actually open up and then replace these, but the maintenance is very, very costly. Hence the reason why nowadays people are actually moving from DC motors to AC motors, because they're more they're not that expensive. Basically, and also it's a good alternative as well. Okay, but the reason why we didn't pick AC DC motors, because with DC motors is much easier for us to control, and there's already a lot of platforms out there that's done by DC motors, so there's less headache for us to deal with, right? Okay, well, let's see. Some of the application for these type of DC motors are like toys, RC servos, and gear motors. Okay, so there you go. Okay, now let's dive into brushless DC motors. So, well, what I want you to first notice is the inside, the differences on the inside motors. Let's look at figure 3. Okay, what you see is that the coils are actually on the walls of the motors, whereas for brush DC motors, the coils are actually in the middle of the motor. Okay, that's the main difference. Essentially, what I'm trying to tell you is that the coils and the permanent magnets are essentially switched position, and because they switch positions, there's no longer need for the brushes anymore. Hence why it's called brushless DC motors. All right, and however, there's a lot of there's a drawback, of course, to this design, and that is and some of the advantages as well. So let's just talk about the advantages, and then we'll talk about the disadvantages after, so we can keep it consistent. Okay, so some of the advantages is that it's much quieter, since there's no sound that's being created from friction. And second, and it becomes more efficient because it's not being slowed down or being heated up from friction as well. So getting rid of those brushes actually gives you a bigger advantages. Okay, so now you ask me, what are the disadvantages? Well, some of the disadvantages of a brushless DC motors is that, well, it doesn't have a good low speed torque. Now, I keep saying this word, and for those who don't know what I really mean, let me explain it a little more visually. Okay, let's just say this is a shaft of your motor and it's twisting like this, right? If it's going really fast, and let's just say you put your hand here and trying to basically prevent it from rotating away of how it should be, and if the motor is still able to rotate and basically like resist the force that you're applying on the shaft, that means that it's actually able to withstand it. It has a really good torque. Let's just say the motor is spinning really slow. Even at slow speed, the robot is still able to move and then basically resist your force. That means that it has a good low speed torque. Now, with brushless DC motors, it's actually kind of the opposite. If you actually put your hand against the shaft and trying to stop it, it will have you're gonna have an easier time actually stopping that motor than when compared to a brushed DC motor. So that's actually the main difference between brushed and brushless, because so essentially that's it, and hence the reason why we actually pick brushed DC motors over brushless. All right, okay. So let's see, what are some of the applications? Well, some of the applications for the brushless DC motors are drones, fans, and that makes sense, right? Because they need really high RPM, which is revolution per minute, right? So with a high RPM, the only force they're actually resisting is air resistance, okay? And which is not that much compared to how much force you're applying with your arm or any load essentially, right? Because air resistance is very light. Air is very light, so hence the reason why it's better for them to be used on projects like drones and fans. Okay, all right. So I know that I skipped some of these like technical terms up here, and that is because you don't really need to know them. I did put them up there, but I kind of already explained it briefly of how these brushless motors are working. Plus this GIF is kind of explaining how it also works as well. So, but if you guys still have questions about what I meant over here, feel free to email me. In the second workshop, since it's going to be live, you guys can also ask me questions about that as well. Okay, let's look at the next slide. All right. Okay, so next we're going to be talking about servo motors. Servo motors are going to be really important in the field of robotics, and so I want you to understand what a servo motors are actually about and what makes it a servo motor, because the terms can actually be used around carelessly, and I want to make sure that you guys are on top of it. Okay, for it to be considered as a servo motor, it needs to have a gearbox, potentiometer, DC motor, and H-bridge. Now these are fancy words for me, at least some of them are fancy words, but I'm going to explain to you that they're not, okay? Gearbox is basically something that when you use to increase torque, to increase power, but it also slows down your revolution, okay? Your RPM of the motor of which you're connecting this gearbox to. Potentiometer is essentially a sensor that gives you feedback of what position of your shaft is at, and your DC motor is essentially, most of the time it depends, okay? There's a reason why it says DC motors. It could be brushed and brushless or AC, doesn't matter, but it has to be a motor essentially, right? Sorry, it has to be a DC motor essentially, not AC, sorry. Now H-bridge is basically a controller that allows you to control what speed the motor should be going at and what rotation, if either clockwise or counterclockwise, or if you want the robot to basically brake, things like that, right? Brake as in not B-R-A-K-E, not like destroy, brake. Okay. All right. So let me show you what I meant by in the picture that I have up here. The picture is this picture usually allows you to see everything what I'm talking about very clearly. So let's see. As you can see, DC motor right here, it has high speed and low torque. What did I tell you? What is it? What kind of motor is this? Well, it's brushless, right? However, like I said, it could be brushed DC motors too, and in fact, the combination of all the components we put together on a robot, you can actually consider as a servo motor. But the trade-off, the difference is that we're not actually using brushless, we're actually using brushed. Hence the reason why they just label it as DC motors, not either brush or brushless. Okay, all right. So since that, what does that mean? Well, it's have a really high speed. I mean, they have a high RPM, so it's spinning really fast. So if it goes to the gear train, obviously the gear train is going to slow it down due to friction and a lot of other components, due to the gear ratio. And then so it dropped down to 60 RPM. Now this number is not fixated. It always depends on what kind of gearbox you have set up. But in this picture, it's the 60 RPM just to show you that it has slowed down. And because of the gearbox, what does it do? It also increases torque. That's really important. So basically, you can actually get a brushless DC motor and still produce a high torque. Okay, potentiometer. Potentiometer is essentially a shaft that's connected to this gearbox and basically gives feedback or data back into the control circuit for it to see whether or not if it's in the right position as it needs to be when a user gives a command of some sort. Okay, so yeah, that's what the potentiometer is. Potentiometer is essentially a sensor. Okay, it's a type of sensor out there that we have. that we're going to be exploring a bunch more sensors that we have on our robots, and that is actually going to be on in our next workshop. So I hope you guys can attend. It's going to be live as well, so you guys can ask me more questions if you guys have any. Okay. All right, so this control circuit here, like I said before, it is you can also call it a motor driver or motor controller or whatever. There is a difference between motor controller and motor driver, and I'll explain it in the upcoming slides when I talk about motor drivers. But for now, this circuit essentially is a motor driver because it's driving the motors, okay? And the I guess the theory that's behind the motor driver is the integrated H-bridge, okay? And we're not gonna go way into it, but essentially this circuit is doing that is either telling the motor to do clockwise or counterclockwise, okay? Once you started programming how to do that, you understand how the H-bridge works. So I'm not going to explain it right now because it's most likely going to be covered in the programming side. If not, you guys can still ask me. I am not in charge of the programming side. I believe RN is a CS lead, and he may or he may not cover this. If he doesn't and you guys are still curious about how it works, come to me. I'm more than happy to go over it. All right. Okay, so why do I have this picture here on the figure 6? Okay, why do I have this picture for the servo motor? Well, AX basically is like is a control loop system. It's a control loop system that kind of explains how the servo motors work. Okay, and all right, here it goes. So input is a user input. That means that I'm actually telling the servo motors to turn at a particular degree, at a particular time, particular speed. Okay, and that can all be written down on your microcontroller, such as Arduino or Arduino Mega or Raspberry Pi, things like that. This is where it's coming from. It's sending the data, and then it gets to the controller, or in other words, it gets to the control circuit, right? And the control circuit is, okay, I get what you're saying, let's do 20 degrees, and it processes it, and then basically tells them it drives the motor to get to 20 motors at a particular speed that you wanted, you indicated in your microcontroller or microprocessor, whatever the case may be that you're using. And what the potentiometer does is that, okay, let's see, am I at 20 degrees yet? It gives you feedback data back to the microcontroller, and the microcontroller compares the destination and where it is at right now. Let's just say I am actually at 15 degrees and I told it to go 20 degrees. So basically it's still it hasn't finished doing its job. So it's gonna keep going. So I was okay, and then and the control circuit sees that. I was like, okay, I'm gonna keep pushing this robot to go at this speed and keep going. And as soon as it hits to 20 degrees, it is gonna stop. Okay, and that's what it does. That's all it is. Okay, that's essentially how the servo motors work. And that's essentially how this is kind of the majority of how most of the motors are controlled as well, especially brush DC motors, okay? And actually most motors out there actually, but yeah. Okay, all right, let's go to the next slide. If you guys have any questions about this, let me know. I am going to go over this a little bit more in detail because we need to for our robot, because that will help you understand how the robot, at least it's set up. Okay, this is actually motors is actually a huge deal, because what you'll notice is that it draws a lot of amps. Okay, that's motors. The electrical component that draws the most amps on a robot right now is motors, and that's important because it depends on what type of battery we have to choose, okay, and what type of motor driver we have to pick as well. So we're going to go over motor driver in this workshop, but we're also going to go over batteries in our third workshop. So don't miss that out. Please attend. It will help. Basically, all of these workshops are going to help you understand what's going on and how the robot is set up EE wise, okay, in the EE perspective. And once you master, at least basically finish the projects that we have, you're going to completely understand how the robot is all wired up and everything. And that's honestly, I gotta tell you, it's an amazing feeling that you're gonna feel so accomplished, okay? And after that, you guys can move on to which any other team you want. I can guarantee you that EE team is mostly going to be the team that's going to get their jobs done first, because we need to get our jobs done first for any for the CS team to even make any progress, right? Because electricity needs to be feed through to the robot so that they can start working and start programming and see how it performs in real life. So it's important that we do finish our job fast and get it done. But at the same time, that also means that we'll get our job done, right? We have to. It's kind of what we have to. That's what we signed up for. All right. Let's go to the next slide. Okay, stepper motors. Stepper motors. There's a huge variety of stepper motors out there. I am not going to go into details because we don't really need to, okay? But I'm going to explain where they're used for, some of the disadvantages, and how it works, okay? But if you have any more questions about this, let me know. If I don't know the answer to your questions, I would certainly find someone who I can direct to that will help you explain it better, who can explain it better, okay? I am getting a little thirsty. Hello. Okay, sorry. All right, let's go. So the inside of the stepper motors is very similar to brushless DC motors, and it's true. It's very similar setup. And the difference is, first of all, the way that the difference is how the coils are actually energized. Okay, they're energized one at a time, and the reason that is because we want to make sure that the shaft or the rotor is called the one that's in the middle. Okay, the one that's spinning is called a rotor. So basically, if it allows you to be very precise of how well the shaft is moving. Okay, you can be like, okay, I want to move at 1 degree at a time, and that is very, very useful in robotics, even more useful than servos at times. Okay, but stepper motors are way much more expensive than servo motors, by the way. Actually, servo motors depends. You can actually kind of work around your budget to kind of see you can get a really cheap stepper motors, or you can get a really expensive stepper motor. So it really depends. When it comes to stepper motors, you can kind of kind of shuffle your money here and there. But when it comes to stepper motors, brushless and brush DC motors, they're kind of like fixed. Okay, they are pretty expensive, but the most expensive one is stepper motors. Okay. Some of the advantages. Well, the advantages are actually shared with brush and brushless DC motor with brush DC motors. Okay, it has good speed, it has good torque at low speed, which is great. It has great positioning, which is what a servo motor has. It has excellent control of rotational speed. So essentially, it has all of the components that you like, all the best components that you want from the previous 3 types of motors out there. Now, yeah, you may ask me, why don't we use this? It's expensive. It's expensive. It's expensive. That's all I'm gonna say. Okay, we don't have that much money to begin with, and we don't want to be putting too much money on just one motor, because there's so many stuff we have to buy for the other types of robots. So if we can work with if we can work with the cheaper parts and still achieve the same thing, that's a plus. Okay, so yeah, that's essentially the main reason. Applications. Another reason we didn't go with stepper motors is because you gotta notice how many wires this thing has. Okay, and there's many varieties of stepper motors out there. It's very confused. It can get very confusing. It also can get very difficult to learn how to control it. But I'm not saying it's impossible. It is possible, but it is going to take time, and which we don't have. So DC motors, easy solution, cheap option as well. So why not go with it, right? Okay, now you may ask, what are some of the applications that these people are using, this motor will be applied in? Well, application will be such as like 3D printers and CNC. CNC is like machining for like manufacturing stuff, and 3D printers again, manufacturing stuff again. So why do we use it here? Well, you gotta know that 3D printers they need to be very precise, because if you want a certain figure to be formed, you have to be very precise of where you want basically the plastic to be melting at a particular spot. So it makes sense why 3D printers stepper motors are used in 3D printers. And I'll be honest with you, the most expensive parts whenever you buy a 3D printer are the motors. It's not like anything else. Like the heat sink and all that stuff, they're very cheap. And for those who are ever going to be making a 3D printer in the future, the only thing that you gotta first look out for is motors and batteries, and the rest is gonna be handled by everything by coding, which is free, right? Most of the time it's free, but yeah. All right, so that's what Servo Motors is, and I'm going to be going over motor drivers after this. But let's look in the overview of 3 motors being compared. I didn't include Servo Motors here again because it's your money can be pushed around here and there, so it doesn't make sense to kind of to put Servo Motors on here because it's kind of ambiguous. So here it is. Here's why we pick brushed. Okay, so we can have good speed control if we have an encoder, and in which we do on a robot. We actually do. Okay, hence the reason why we invested our money on an encoder. And speed control will be better. Positioning control will be better. And the cost is really cheap. So, and it is a little bit more expensive with encoder, but you don't. But it's not as expensive as a stepper motor, right? You can still see that. So it doesn't make sense to buy a stepper motor. And brushless, we all know it doesn't really apply to us. So there you go. Brush is all you got. Okay. All right, motor drivers. Let's see. I gave you guys 2 common motor drivers that we use on campus. There's many types of out there, and you have to make sure that the motor that you picked works with the driver. Okay, that's very important. If it doesn't, then you'll realize that your motor is not going to be moving at all. It will be moving, but not in a way you want it to be. Okay. All right. So now you might ask, why do I pick this over? Why do I pick? Why did I not pick this, but I picked this instead? Well, there's a lot of specification here. Okay, and I am, but they do not all matter when it comes to picking why we pick. Only one of the specification is the basically the main factor of why we pick one over the other, and that is the driver current or current draw. Okay, that is very important. Okay, and I'm gonna come back to this slide and you'll see why. So I'm gonna go to the next slide and come back to this slide, and you'll see, you'll understand why I picked this one over the other one. Okay, but and we already have this on campus, so we don't want to purchase a new one, so that's why we picked this one as well. But let's go to the next slide and I'll explain. So okay, so this is the motor that we picked. Try to memorize it. Oh, you don't have to memorize it, but try to learn about it. Okay, this picture that I added is actually from the website of this motor, and this is a spec sheet it gave us. Okay, every spec sheet is never going to be the same, so you guys always have to be learning how to read a new data sheet every single time, so keep that in mind. All right, so first of all, it wants 12 volts. Okay, that's great. That's not bad. That's very standard. It's not absurd weird looking number, so we're off to a good start. All right, it says right here there's a typo in the data sheet, but that's okay. We don't really care much about that. It says no load. What does that mean? That means that when the motor is turning, there is no resistive force on the shaft of any kind, and when it is so at that particular condition, the motor can go at this speed and it's only going to draw 2.5 amps, which is not a lot. Okay, your USB-C can draw up to 3 amps, so that's very low amp draw. Okay, at stall. Okay, at stall is exactly like the exact opposite of no load. It actually has a huge amount of load, where even when the robot is still able to move, but it's struggling a lot. Like it's struggling a lot to a point where you're actually able to stop it, but still it still has a lot of torque, but it took a lot of power to kind of stop it. And at that particular conditions, it's drawing about 131 amps. that is huge, a lot of draws, okay? It's drawing a lot of power. Okay, so I shouldn't use the word power because power is voltage times current. So, okay. But yeah, it's drawing a lot of current. And I do have to warn you, it's not the voltage that kills people, it's the current, okay? The larger the current, the more dangerous your project is going to become. But right now, this is still pretty small, but but you can still get shocks, okay? In fact, if you actually use your iPhone charger to like type of wire, which is very kind of thin, right? What you're like, and if and it's drawing about 131 amps, what's going to happen to you is that, well, the wire is going to be burning really hot, and eventually it's going to like rip apart the plastic. I mean, not plastic, basically like the rubber on the wire is going to burn off and then start catching up on fire, okay? And you don't want that, because we don't want our robot to be on fire. That is not good. So that's like the worst case scenario, and we never want that, or we never want our robot to experience that. So we always have to keep that in mind. Never let the robot get to this particular condition ever. All right. Now the next two parts are the most important ones. I'm at maximum efficiency. What does that mean? It essentially means that you're getting the best power you can possibly get at a very minimal amp draw, and that's, in this case, is where you have 18 amps and you're getting about 283.5 millinewton meters. So if we convert that to just newton meters, that's basically saying 0.293 newton meters, which is, and honestly, it's not a lot, because if a robot weighs like 80 pounds, oh my god, that's not gonna carry, the robot is not gonna be able to move that thing at all. So what do we do to account for that? Well, we bought a gearbox, okay? The gearbox, again, when I tell you it increases your torque, but it reduces your speed, okay? So that's a drawback right here. So most likely your robot is going to draw a lot more amps, probably 18 or 20 or 30 amps, and then still able to achieve this amount of but a higher level of torque, okay, due to the gearbox. And we have a gearbox. We bought it from the same company, AndyMark. It was rather pricey too, so whenever we work with these parts, always be careful. If you have any questions, either ask me or refer to the manual, okay? Essentially, that's how it's going to get done. Okay, at maximum power. Okay, at maximum power, all we care about is like power is this, okay? This is how much power it can draw. It also like increases your torque. It also increases your amp draw, because if you want more power, which is voltage times current, you're also increasing your current, and while your voltage is gonna stay constant. Okay, so that's the important part. Yeah. So what you gotta notice is that we may be going up to here because we want maximum power at one point. If the robot needs to get there. So 66 is kind of where we're gonna push our, that 66 amp is where how much amps our motor driver it needs to handle, okay? And because of that, right here, because of that, we have a peak current of 80 amps for this motor driver. Over here, there's no peak amps. It's still going to be drawing at 2 amps. So what's going to happen if you let this little circuit right here to control the motor that we have on a robot, it's going to blow up, okay? It's going to heat up and explode. We don't want that. We don't want that at all. So because of that, we picked this one, and it's much better. And it even has like additional features, like, you don't have to code anything. Oh, you do have to code something, but like you can actually test the motors if it works, if what we're doing, if the wiring is set up correctly by essentially pushing buttons on the circuit board. There's buttons on here. I don't really see in the picture, but yes, right here and right here. Those are the two buttons. If you press those two buttons, you can actually control the motor manually and test it to see if you have wired it up correctly or not. So that's a really cool feature, and really easy to work with. Okay, so basically that's why we picked this motor driver, and this is why we picked this motor is because it has good low speed torque, and it's very easy to work with. So yeah, that's how it's set up right now on our robot. And yeah, I didn't really go over much about torque and why we picked this motor. I am going to explain that in person and live, because it's better, because we're going to have physics involved, and I want to draw like free body diagrams and explain how we kind of calculate and everything. So yeah, it's better to be in person. So if you guys have any questions, and it's better to be more engaging for those tougher problems, I guess, to show you guys. But yeah, I'm gonna do that live. And if you guys have any more questions about this, of anything what I've gone over in the slide, feel free to email me, or just simply come to the next workshop and ask me those questions, okay?